Welcome to the Deep Dive. We're here to cut through the noise and get you the essentials from key documents. Today we're tackling something I think many network admins know all too well, that feeling, right? Your router, that usually silent black box, just stops. And suddenly it's panic stations. That fight or flight kicks in because, let's face it, these Cisco doxes often just work until they don't. And then you realize you haven't really dug into it. So our mission today, we're pulling the absolute must-knows from Cisco Routers for the desperate second edition. The goal is to take you from that headless chicken moment to feeling, well, actually comfortable managing your network.
Exactly. And it's not just a command cookbook. We need to understand why we're doing things. What are the implications? We'll go from, literally plugging it in for the first time all the way through redundancy, security, giving you that context so you feel genuinely comfortable inside the Cisco environment.
Okay, let's do it. Let's unpack this thing. Picture that new router arriving. First things first, before you even plug in the power, you need to connect. That means grabbing that flat blue console cable, right? Usually RJ45 to a DB9 serial adapter for your laptop or terminal server. And here's warning number 1, highlighted in book. Do not power it on yet. Get connected first so you can see everything.
That's really good advice. You want to see the boot sequence. So yeah, get your serial client ready first. Hyperterminal if you're still on older Windows, or maybe PuTTY or TIP or Q on Linux or macOS. And the settings have to be spot on. 9600 baud, no parity, 8 data bits, 1 stop bit. No flow control. That's your window. Oh, and don't mix up the console port with the auxiliary or O port. Looks similar, but the O port won't show you those crucial boot up messages. It's more for like backup remote access later.
Right. So connected, settings are good. Then we power it on. You see all the boot text scroll past, and then you hit that question. Would you like to enter the initial configuration dialog? Yes, no. The book strongly advises saying no here. Why skip the guided setup? Seems easier, no.
Well, easier isn't always better, especially for control. The command line interface, the CLI, it's universal on Cisco gear. It gives you absolute control, full visibility. That initial dialogue can be kind of restrictive, might hide things. When you say no, you land at the router prompt. That's EXEC mode. Good for looking around, basic checks. But to actually change anything, you type enable. That bumps you up to a privileged EXEC mode, and your prompt changes to router hashtag.
The # mode, that's where the real work happens.
Exactly. And because it's powerful, you absolutely need to protect access to it with a strong enable password, or better yet, an enable secret. We'll get to that.
Okay, but what if you're staring at that router hashtag prompt and drawing a blank? Is there like a help function?
Oh yeah, absolutely. The question mark is your best friend. Just type it. Router hashtag prompt shows you all the commands available in that mode. Or type part of a command then, like show fei, and it lists all the things you can show. It's context-sensitive help built right in. And another time saver, command abbreviation. Once you know the commands, you can often shorten them, like she instead of show. Saves a lot of typing.
Nice. Okay, command line basics covered. Let's get into the router's actual brain. How does it think about its configuration?
Right, this is fundamental. The show version command is your starting point. It tells you so much, the iOS software version, which is critical, the hardware model, how much RAM it has, and maybe my favorite bit, the uptime. Seeing something like uptime is 4 weeks, 4 days, 9 hours, 53 minutes can be, well, reassuring when things are acting up. Tells you the router itself probably isn't the thing crashing every 5 minutes.
Good point. Stability check. Now, the book makes a really big deal about 2 types of configuration. Running versus startup.
Yes, absolutely critical distinction. The running configuration is what's live right now in the router's RAM. It's volatile. Power cycle the router and poof, it's gone. The startup configuration is saved in NVRAM, non-volatile RAM. That's what the router loads when it boots up.
Ah, okay. So any changes you make
Are only in the running config initially. You have to explicitly save them to the startup config if you want them to survive a reboot. Think of it like editing a document. The changes aren't permanent until you hit save.
Makes sense. So how do we see these configs, and crucially, how do we do that save?
Easy enough. Show running config, or run for short, shows you what's active. Show startup config, or start, shows the saved version. And to save, the command is copy running config, startup config. You'll often see people use the older command write memory, or just RAMMEM does the same thing. Muscle memory for a lot of folks.
Copy, run, start. Got it. And backups.
Oh, definitely. Best practice is to regularly copy your running config off the router entirely to a text file on your laptop, or even better, automate backups to an FTP or preferably an SCP server. Lifesaver if things go really wrong.
Okay, so we want to make a change. We've figured out running versus startup. How do we actually enter configuration mode?
You check configure terminal,
Uh,
or the shortcut everyone uses .config.
config.
Your prompt will change, usually to router config hashtag. That tells you you're in global configuration mode. From there, you can target specific things like type interface fast ethernet 01 or int faz01, and your prompt changes again, maybe to router config hashtag. That means commands you type now apply only to that interface.
Oh, so the prompt tells you your context.
Exactly. Or if you configure a routing protocol like router BGP 65000, the prompt might become router config router hashtag. It's a really helpful visual cue. You see it reflected in the saved config file too, with indentation.
Okay, configuration modes make sense. Now, routers connect networks, so interfaces are key. How do we see what ports we even have?
Show interfaces. That gives you a rundown of every interface on the box, physical and logical. You'll see names like Fast Ethernet 10, meaning the first Ethernet port on module 1, or Serial 00, and again, abbreviations usually work, like FAT10 or CEDAR 1000.
Then the output of show interfaces. It looks pretty dense. What are the key things to look for?
Yeah, there's a lot there. First, look at the first line for each interface. It'll say something like, Fast Ethernet 10 is up, line protocol is up is what you want. The first up means physical link cable plugged in, seeing electrical signal. The second up, line protocol, means it's successfully talking layer 2, like Ethernet framing is working, or HDLC or PPP on a serial link is established.
So up is good. What if it's like up-down?
Up-down usually means a configuration mismatch. Physical connection is there, but maybe the encapsulation type doesn't match the other side, or clocking is wrong on a serial link. Down-down means likely a physical issue, bad cable, port shut down, other end powered off.
Got it. What else in that output is important?
The description field. Use it. Add a description to every important interface, like description main office LAN or description ISP uplink circuit ID 12345. It makes troubleshooting so much easier later.
Good tip. Self-documentation.
Absolutely. You'll also see the IP address and netmask if configured, the MTU size, usually 1500 for Ethernet, may be different on WAN links, bandwidth, BW, and that crucial encapsulation type. RPA for standard Ethernet, maybe PPP or HDLC for serial links. Remember, encapsulation has to match on both ends of a point-to-point link.
And the classic gotcha. Interfaces are off by default, right?
Yep. Administratively down or shut down. To turn an interface on, you need to go into its configuration mode, int faz01, and type no shutdown or no shut.
No shut. Never forget no shut.
Never forget no shut.
So for an Ethernet interface, configuring it is basically IP address, description, no shut, anything else.
Generally, that's the core. You might see no IP-directed broadcast. That's a good security practice. Stop certain old denial of service attacks. And speed and duplex. Honestly, leave them on auto unless you have a very specific reason not to, like troubleshooting a known issue with an older device. Forcing speed and duplex manually when it's not needed is a common source of weird, hard-to-diagnose problems. You'll be asking, who was the idiot who set this?
And the answer is usually.
Usually you, 6 months ago, trying to fix something else. Auto-negotiation usually works fine these days.
Okay, that covers local Ethernet. What about connecting to the outside world? WAN links, serial interfaces.
Right. Serial interfaces are the workhorses for traditional WAN connections, like T1 lines. They're simpler in concept than Ethernet, usually just point-to-point between two devices. Configuration is similar. AB address, encapsulation, like PPP or HDLC, description, no shut. Sometimes you need clock rate settings if you're providing the clock signal, but often the telco equipment handles that.
You mentioned logical interfaces earlier too, loopback and null.
Yeah, briefly. A loopback interface is purely virtual. It's always up. Routers use it for things like BGP source addresses or management access because it gives the router a stable IP that doesn't depend on a physical interface being up. But don't just create them unless you have a specific need. And a null interface, usually null 0, is like a data black hole. Anything routed to null 0 just gets discarded immediately. Sounds weird, but it's useful for things like preventing routing loops or for black holing traffic in BGP.
Okay, so putting this together, how do we actually connect our office to the internet using this stuff?
First step is choosing an ISP. The book mentions different types: big telcos, national providers, regional ones, smaller local shops. Regional can often be a sweet spot for service and price. Crucially, you need info from the ISP. What IP addresses will they assign for your side and their side of the serial link? It's often a 30 subnet. What's the circuit ID for reference? And what encapsulation are they using on their end? PPP, HDLC. You need this info.
Right. Can't configure without the details, assuming we have them.
Okay, so on your router's serial interface facing the ISP, configure the IP links as they gave you with the 30 subnet mask, set the encapsulation to match theirs, add a good description like ISP link circuit XYZ, and no shut.
Then configure the internal Ethernet interface facing your LAN with its own IP address.
Exactly. And the final piece for basic internet access is the default route. IP route, base.0.0.0.0.0.0, followed by the IP address of the ISP's router on the other end of your serial link. That tells your router, send anything you don't have a specific route for out to the ISP.
And then,
Copy run start or rearm immediately. Don't lose that config.
okay, that's internet. What about connecting two offices directly, say with a private T1 line?
Very similar process, but instead of a default route, you'll use private IP addresses, those RFC 1918 blocks like 10.x.x, 172.1631.x.x, or 192.168.x.x. You'll need to subnet appropriately, probably using a 30 for the point-to-point T1 link itself. So one IP for your router, one for the router at the other office.
Routing between them, static routes.
For simple setups like just two offices, yeah, static routing is often the easiest and most reliable. Dynamic routing like OSPF or EIGRP is possible, but might be overkill. The rule is the router always chooses the most specific route. So a route to a specific internal network will always be the default route to the internet.
So how would that look? Let's say HQ in a remote office.
Okay. The remote office router needs a route back to HQ's network. Let's say HQ uses 10.1.0.016, and the T1 link uses 10.0.3.430, with HQ being 10.0.3.5 and remote being 10.0.3.6. On the remote router, you might just set a default route pointing to the HQ router across the T1 up route 0.0.0.0.0.0.0.5. Simple.
And at HQ?
At HQ, you need a specific route to the remote office's network. Let's say the remote office LAN is 10.0.2.0.6. HQ still needs its own default route pointing out to the internet, maybe via a different interface or router. But this specific route ensures traffic destined for the remote office goes over the T1.
Got it. Most specific route wins.
Okay.
Configuration basics covered, but what happens when things break? That mysterious black box moment.
Troubleshooting. Yeah, that's when the panic sets in if you're not prepared. The book kind of splits this into two camps, the router itself crashing or the network connection failing.
Let's take router crashes first. What can you do?
If the router itself is rebooting or freezing, first thing is get on that console port, see if there are any error messages scrolling by just before it dies. Copy those down exactly. Then Google those error messages, search Cisco's website, maybe try reseating module or memory inside the router carefully, but honestly. If the hardware seems to be failing, this is where having a SmartNet support contract is absolutely golden. You'll likely need Cisco's help, maybe an RMA.
Right, SmartNet for hardware issues.
Yeah.
What about the more common scenario? The network connection is down, internet's out, can't reach the other office.
First question, always. Did I change anything recently? If you just made a config change, undo it. See if the problem goes away. Configuration errors are super common.
Good point. Rule number one of troubleshooting. If that's not it,
then break out your basic tools. Ping and traceroute. Can you ping your default gateway? Can you ping the other end of the serial link? Can you ping something reliable on the internet, like 8.8.8.8? Ping gives you those exclamation marks for success or dots for failure. Simple, but tells you a lot about basic reachability. Traceroute, or traceroute on Windows, shows you the path hop by hop. If it stops somewhere, that hop might be down or blocking traceroute. If you get H, that means a router along the path doesn't know how to reach the destination. Essential tools.
So ping and traceroute help isolate where the break is. What about looking at the interface itself?
Absolutely. Back to show interfaces. Check that up-down status again. Did I up, down, down, down. Remember the smart jack that's the telco's demarcation point where their responsibility ends? And the CSU-DSU, the device connecting the smart jack to your router's serial port. Problems can happen there too. Show interfaces also gives you error counters. Look for things like input errors, CRC, frame, overrun, ignored. A small number might be okay, but if they're rapidly increasing, that points to a line quality problem, maybe noise on the circuit, or a physical layer issue.
What can you do if you see errors climbing?
First, try resetting the interface. Go into config mode, config to T, in CODO, do a shutdown, wait a few seconds, then no shutdown. Sometimes that clean is temporary glitches. You can also use clear counters CO1000 to reset those error stats to 0, then watch show in CO1000 again for a few minutes to see how quickly new errors appear. It gives you a fresh baseline.
And if resetting the interface or even rebooting a router doesn't help and errors keep climbing,
Then it's probably time to call your ISP or telco provider. But go in armed with information. Tell them, my interface is showing increasing CRC errors, or my line protocol is flapping, or I see lots of carrier transitions. Give them the output from show interfaces.
Makes the call much more productive than just, the internet is down.
Exactly. The book also mentions extended pings, which can be really useful for diagnosing tricky line issues.
Extended pings, how do they work?
You just type ping and hit enter. It'll ask for the protocol, target IP, repeat count, etc. But then it asks extended commands.no, type Y for yes. Now you can do cool stuff. You can set the data pattern, like 0x0, 0000000, or zeros SFFF, all ones. Some older line encoding types have trouble with long strings of zeros. You can also sweep range of sizes. This sends pings of increasing size, maybe from 100 bytes up to 1,500 or 18,000 bytes. This can find problems where, say, small packets work fine, but large ones fail, pointing to MTU issues or fragmentation problems somewhere.
Oh, okay. So you can test specific problematic patterns or sizes.
Right. If you can tell your ISP standard pings work, but pings with data pattern 0000 fail, or pings over 1,400 bytes fail, that gives them very specific clues to investigate encoding mismatches, like AMI versus B8ZS, or MTU path discovery issues.
Good tools to have in the toolbox.
Yeah.
What about loopback tests? Telcos always want to do those.
Yeah, they love loopback tests. It lets them test their circuit up to the smart jack.
Yeah.
Just be aware, when they put the circuit in loopback, it will completely disable your circuit. Your interface will go down, so schedule it if needed. Don't let them do it randomly during production hours.
Okay. And if the loopback test passes clean on their end, but you still have issues?
Well, then the problem is likely yours. Check your internal cabling from the smart jack CACSU to your router. Maybe try a different router port if you have one. If you're convinced it's the router hardware, back to that SmartNet call.
This all highlights the pain of outages. How do we build in resilience to avoid this drama? Redundancy.
Exactly. Now we're talking proactive network design. The first big step for internet redundancy is usually BGP, the Border Gateway Protocol.
Right, BGP lets you have connections to multiple ISPs.
Correct. BGP operates between autonomous systems, or ACs. Big networks like ISPs, universities, large companies, they each get an ASN, an autonomous system number. These ACs peer with each other and exchange route announcements. They basically tell each other, I know how to reach these IP address blocks. They also include the AS path, the list of ASNs the announcement has traveled through.
And how does the router use that?
Your router listens to the announcements from its BGP peers, your ISPs. To reach a destination, it generally picks the path with the shortest AS path. Fewer AS hops is considered better. But here's a key point. BGP is not inherently a load balancing protocol. It doesn't care if one link is a 10 gig pipe and the other is a slow T1. It just looks at the AS path length usually. So traffic might heavily favor one link, even if the other has capacity.
Okay, so it's for failover, primarily. What do you need to actually run BGP?
There are prerequisites. You need a router with enough memory. The book suggests at least 512 MB RAM, maybe more now as the global BGP table keeps growing. You need at least 2 ISPs willing to give you a BGP feed. You need your own block of IP addresses, usually a 24 or larger, that's portable between ISPs. And you need your own ASN, which you get from your regional internet registry like ARIN, RIPE, or AT&I, plus usually a routing registry entry.
So a bit of administrative overhead to get started?
Definitely. It's not something you just switch on casually. But the redundancy is huge.
How's the basic configuration look?
You'll define an access list that permits only your IT block. You'll create a static route for your entire block pointing to the null zero interface. This ensures you always originate the route. Then you enable BGP router, BGP, your ASN. You configure your neighbor statements, telling your router the IP address of the ISP's router and their ASN, remote as their ASN. And critically, you use route maps applied to your neighbors to control which routes you announce out, usually just your own IP block defined in that access list, and potentially filter what routes you accept in. The book is a good example config to study.
How do you check if BGP is working?
Shoproute BGP summary is your main command. It shows your neighbors, their ASNs, how long they've been up, and how many prefixes routes you're receiving from them. Shoproute IP address will show you the specific route being used to reach a destination, including the BGP learned path and which neighbor it came from.
You said BGP isn't load balancing, but can you influence which link gets used more?
Yes, you can influence it. It's often called traffic engineering. A common technique is AS path prepending. To influence inbound traffic, how others reach you, you can make your announcement look less attractive to one ISP by artificially lengthening the AS path. On your route map going out to ISPA, you might add set as path prepend, your ASN, your ASN, your ASN. Makes the path look 3 hops longer via ISPA, so ISPB's path might become preferred.
Ah, clever. Make one path look longer.
Exactly. To influence outbound traffic, you might prepend the ISP's ASN on routes you receive from them, or use local preference attributes. But AS path prepending is common for influencing inbound flow.
Any pitfalls with BGP?
Be very careful with clear if BGP commands. Resetting a BGP session too often can cause route dampening. Other routers see your routes flapping and might temporarily ignore them to protect their own stability. It's like putting your rights in timeout. Also, remember, BGP convergence isn't instant. It can take minutes, sometimes up to 20 minutes, for changes to fully propagate across the internet. Patience is required.
Okay, BGP handles ISP redundancy. What about the router itself failing? One router, even with 2 ISP links, is still a single point of failure.
Good point. That's where HSRP, the Hot Standby Router Protocol, comes in, or VRRP, a similar standard. HSRP is Cisco proprietary. HSRP lets you have 2 or more physical routers act as a single virtual router from the perspective of your internal network clients. They share a virtual IP address, VIP, which you use as the default gateway on your servers and workstations.
So if the active router fails,
the standby router detects the failure and takes over the virtual IP address and virtual ASI address seamlessly. Your internal clients don't even notice. They just keep sending traffic to the same default gateway IP.
nice. How do you configure HSRP?
It's actually pretty simple on the interface facing your internal network. On both routers, you configure the same standby group number and the same virtual IP. Standby 1 IP 192.168.0.1 using your desired VIP. Then you set priorities. Standby 1 priority 110 on your preferred primary router and leave the default priority 100 on the backup. Higher priority wins.
Can you tune it?
Oh yes, standby 1 preempt is important. It means if the primary router fails and then comes back up, it will take back over the active role. Without preemption, the backup would stay active. Standby 1 track serial 1020 is also crucial. This tells the router, if my WAN interface serial 1000 goes down, decrease my HSRP priority by 20. This ensures failover happens if the WAN link dies, not just if the router itself crashes. You can also add delay, standby 1 preempt delay minimum 60, so a router waits a bit after booting before trying to become active, allowing BGP and other protocols to converge first. And authentication, so routers only listen to HSRP messages from trusted peers.
So with HSRP and BGP, you need both routers talking BGP to both ISPs.
Ideally, yes. But you also need the 2 HSRP routers to talk BGP to each other. This is called internal BGP or IBGP.
Right.
So that both routers know about all the available paths out via both ISPs. If router A learns a path via ISP1, it needs to tell router B via IBGP. If router B learns a path via ISP2, it tells router A. This way, even if router B is the active HSRP router, it can still send traffic out via router A's connection to ISP1 if that's the best path. You configure this with neighbor internal IP of other router remote as your ASN, and often neighbor internal IP of other router next hop self.
Okay, that gives true redundancy for hardware and links. What about keeping the router software up to date? iOS upgrades.
Right, iOS upgrades. Necessary evil sometimes. You upgrade for security patches, bug fixes, maybe new features, but upgrades are risky. A bad iOS image or a mistake during an upgrade can turn your expensive router into a brick. This is another area where that SmartNet contract is absolutely vital. You get access to download the software legally and access to tax support if things go wrong.
So plan carefully. What's the prep?
Have a reliable way to transfer the iOS image file, like an FTP or SCP server. Have your console table ready just in case. Choose the right iOS version. Don't just grab the latest bleeding edge release. Check Cisco's site. Maybe see what TAC recommends for your hardware platform and features. Look for the stable or recommended releases. Before you start, back up your current running config. And also find out the exact file name of the current iOS image running. Show version tells you the system image file. Maybe even copy that current image off to your server as a backup file.
Okay, got the new image file. How do we load it?
Use the copy command.copy scp.user at serverpath new-ios-image.bin flash, or copy ftp.flash copies the image file into the router's flash memory. You might need to delete the old iOS image first if flash memory is tight. Delete flash.oldios-image.bin. Double check you have enough space before deleting.
Image copied to flash. Then what?
You need to tell the router to boot using the new image next time. You might use the boot system flash.newios-image.bin command to specify it in the config, then save the config, wrmem, and then the moment of truth. You type reload and confirm. Watch the console output very carefully as it boots.
And if it doesn't come back up? If the new image is bad?
Disaster recovery time. If you have the old image still in Flash, you might be able to interrupt the boot sequence, usually crawl break, and boot it manually from the Ramen prompt. If the Flash is wiped or corrupt, you might have to use Xmodem over the console cable to slowly load a working image back on. Painful. Or, frankly, call Cisco TAC and say those magic words, "I am completely down." They can guide you through recovery.
Okay, upgrades require care. Let's shift gears slightly. Cisco devices don't live in isolation. How do they integrate with other network gear, especially switches?
Good question. Cisco switches, especially Catalyst switches, share a lot of the same iOS command structure as routers. If you know the router CLI, configuring a switch will feel very familiar. The main difference is focus. Switches have lots of Ethernet ports for LAN connectivity. Routers handle the WAN links and complex routing protocols like BGP, though high-end switches can do routing too, layer 3 switches.
What are key switch-specific configurations?
Spanning tree protocol, STP, is crucial. It prevents network loops if you accidentally plug cables in wrong. You'll want it enabled, usually spanning tree mode rapid PVST for faster convergence. And on ports connected directly to user PCs or servers, access ports, you enable spanning tree port fast. This lets the port come up immediately without waiting for STP calculations, but it also has a safety feature, BPDU guard, usually enabled by default with port fast, that shuts the port down if it detects another switch plugged in, preventing a potential loop.
Andy, what about discovering neighbors?
Cisco Discovery Protocol, CDP, is great for that. On a Cisco device, Show CDP Neighbors tells you about directly connected Cisco devices, their host name, model, which local port they're connected to, and which port on their side. Super useful for mapping things out.
But potential security risk.
Potentially, yes. It reveals information about your infrastructure. Best practice is to disable CDP on interfaces facing the internet or untrusted networks. You can do it globally with no CDP run, or per interface with no CDP enable. Keep it running internally where it's usable.
How can you track down where a specific user or server is plugged in on the switch?
Classic task. You usually know the user's IP address. First, ping the IP to make sure it's online and populate the ARP table. Then, on the router or layer 3 switch for that subnet, use show ARP include IP address, or I for include. That gives you the MC address associated with the IP.
Got the MC address? Now what?
Go to your switches. Use show MAC address table, include MS address chunk. You only need the last few characters of the MSC address usually. This command tells you which switch port the switch last saw that MSC address on. Follow the chain until you find the access switch and port they're plugged into.
Nice. IP to MSC, MSC to port. Okay, let's talk access security. Logins, passwords.
Super important. You manage access via the lines. Line con 0 for the console port, line O0 for the O port, and line 5i04 or 0 Vecine, etc. for remote access like Telnet and SSH.
What security should be on those lines?
First, use service password encryption. This weakly encrypts passwords stored in the config file, so they're not plain text. It's not strong, but better than nothing. On the lines themselves require authentication with login. For simple password protection, you can set your password directly on the line. But for the enable command, do not use enable password. It uses a very weak, easily crackable encryption. Always use enable secret, your strong secret. This uses a much stronger MD5 hash.
Enable secret, not enable password. Got it.
Even better than line passwords is using local usernames. Define users with username Bob privilege, 15 secret Bob's password, username Alice privilege, 1 secret Alice's password. Privilege 15 is full access, lower levels are restricted. Then, on the lines, use login local instead of just login. This forces authentication against the local username database. More secure, better accountability.
And for remote access, Telnet is bad, right?
Telnet is terrible. Sends everything, including passwords, in plain text over the network. Absolutely avoid it if you can. Use SSH Secure Shell instead. It encrypts the entire session. To enable it, you need a few things. A host name, and if domain name can be fictional, like mydomain.local. Then generate RSA keys with crypto key generate ARSA. Choose a key size, maybe 2048 bits. Then you might want to tune SSH settings like ipstash timeout 60 seconds and ipstash authentication retries 3. And the crucial part, on the line ipatitive or 4, set transport input tush. This tells the VTY lines to only accept SSH connections, disabling Telnet, or transport input tush Telnet if you temporarily need both, but aim for SSH only.
Excellent. SSH is key. What other network services does the router offer that are important?
A few essentials the book highlights. First, auto-secure. It's a script built into newer iOS versions. Just run auto-secure in privileged mode. It asks some questions and applies a bunch of basic security hardening configurations automatically. Good starting point.
Okay, easy win.
What else? NTP, Network Time Protocol. Accurate time is critical for logs. Configure the router to sync with reliable time servers. NTP server, IP address of NTP server. Set your time zone clock, time zone PST8, and daylight saving clock, summertime PDT recurring. Check sync status with show NTP status.
Accurate logs are happy logs.
Speaking of logs.
Yes, logging. By default, logs might just go to the console or a small internal buffer. Configure timestamps, service timestamps, debug datetime MSEC local time show time zone, service timestamps log, datetime MSEC local time show time zone. For better logging, send them to a remote syslog server. Logging trap, debugging, sets severity level. Logging facility local 3 helps categorize on the server, and logging server IP address. Now your logs are stored centrally and persistently. And finally, monitoring, SNMP.
SNMP, Simple Network Management Protocol, allows monitoring tools like SolarWinds, Nagios, PRTG to query the router for status information, interface traffic, CPU load, memory usage, etc. Configure it carefully for security. Use an access list to restrict who can query. Access list 1, permit your management station IP, then apply it. SNP server your community string RO1. RO means read-only, which is much safer than read-write, RW. Choose a strong, non-obvious community string.
Wow, okay, that was a lot, but incredibly thorough. We've really gone from that initial, oh no, the router's down, panic, to understanding the console, configuration basics, troubleshooting steps, building redundancy with BGP and HSRP, securing access, and enabling key services. That's a huge leap.
It really is. And the key takeaway, I think, is that knowledge really is power here. Understanding the why behind these commands lets you move beyond just fixing immediate problems. You can start building a network that's genuinely more robust, more secure, more resilient. It's about going from reactive to proactive.
And like any deep dive, the more you learn, the more you realize there is to learn. So keep digging into those resources, Google, Cisco Docs, and definitely leverage that SmartNet contract if you have it.
Absolutely. And maybe a final thought to leave you with. Once you've tackled ISP redundancy with BGP and router failover with HSRP, your network is significantly more resilient. But it probably still has single points of failure elsewhere. So the question becomes, what's the next single point of failure you're going to address now that the core routing is more solid, pushing that resilience boundary further out?
That is a great question to ponder. What's next on the resilience journey? Thank you for joining us on the deep dive. Hopefully you feel much better equipped to handle your Cisco gear now. Go apply that knowledge.